We have we cover different types of signals, different operations, and we talked about warrants. Then we covered signal terminologies, a quick method of calculating the condition of the signal, critical movement analysis. Then this is the procedure we are going through, and we have reached up to step number 5, which is to find out signal timings if it is an actuated signal. Okay. Now we are moving on to the calculation of capacity to calculate the volume capacity ratio. Okay, so N is, so we are doing it for each group. So in the last step, we calculated saturation flow rate. And the example which we did had 2 lane groups in one direction. Similarly, it would be done for each lane group from all directions. Not each one of them, but the most critical one. And we will discuss this critical aspect in the coming lectures. So what do we mean by critical lane group? So in the previous one, so we had 2 lane groups, right? This one and then this one. Okay, so you need to see which one is more critical for the signal design. If you are allowing all these lanes to go in the same phase, then you cannot design for this one and this one and this one, all of them together. You have to pick one of them as a critical one. Okay, and then the volume capacity ratio of the critical one becomes the design basis. Okay, so as you have seen, there was a lane group with 2 lanes, so N will be 2 in that case. Saturation flow rate is per lane by default, so then you multiply, and then you have the G by C ratio. G is effective green, which is green without the lost time, and C is the cycle length of the signal, total cycle length. So this will give you the capacity of the signal, and then you divide the flow rate of the lane group with the capacity. Okay, so then you get the volume capacity ratio. X is your volume capacity ratio. Once you have done that, the level of service for a signal depends upon its delay. Okay, so this is the relationship between delay and level of service. And how do we get this value? This value is a combination of 3 factors. Okay, we have control delay D1, we have D2, which is uniform delay, and we have D is the control delay, D1 is uniform delay, D2 is incremental delay, and D3 is initial Q delay. The one which we normally see throughout the day is D1, control delay, the delay which is caused because of the signal. So you come to the signal, you have to slow down, you have to stop in the queue, and then signal becomes green, you move, and you take some time to get back to your speed. That is control delay, the most obvious one, the most common one. But there are conditions in which D2 and D3 can be applied, and these are rare conditions, so we will not discuss their calculations here. We will limit ourselves to D1 only. So what is D2 and D3? When the queue is very long at the signal, so every additional vehicle in the queue causes improportionate amount of delay. So for example, the control delay is 2 seconds per vehicle. Okay, but when the queue is very long, if you add 1 vehicle in the queue, the delay will not increase by 2 seconds. It will increase by something more than 2 seconds. So that something more is called as incremental delay. Okay, so when the queue gets very long, the relationship between the number of vehicles and the queue length does not remain directly proportional, does not remain linear. Okay, so adding 1 vehicle can make 5 seconds of delay, another vehicle can make 7 seconds of delay. So it keeps on increasing, by the way. It keeps on increasing. So when the queue is longer, every additional vehicle causes or increases the delay by multiple times. So that is called as D2, incremental delay. And then we have D3. So when you join the signal, there's already a long queue. Okay, so this is the initial Q delay. So even if you joined at the green time, if the signal is green, you cannot accelerate because you already have a long queue in front of you. So that's called a initial queue delay. Okay, so you can see D2 and D3 are both related to oversaturated conditions. Okay, condition in which the queue is very long. Okay, so that's why I said they are rare cases, and we will not discuss them. We'll discuss the normal case, which is D1. So for our case, we are saying D equals to D1. Okay, so how do I calculate D1? You can see the equation over here. Okay, in this equation you see the progression factor here. Progression factor, we already I believe we calculate, no, this is the progression factor, sorry for that. So this whole thing is a progression factor. Okay, so in this equation, so first of all, in this equation we know everything. Progression factor comes from here. C is the cycle length, and G is the effective gain, and X is volume capacity ratio. Okay, then for the progression factor equation, we have G by C. We have the P value, which is the proportion of vehicles arriving during green. It comes from here. Okay, RP value taken from the table, and then you have G by C ratio again. So G by C is a very important factor. Okay, so P comes from the previous equation. Then we have gamma. Gamma comes from here. Okay, so and this is P multiplied by C. Okay, so PC is not something new. This is P multiplied by C upon G. Okay, and then you will see many places minimum of 1 or X here, here, here. Okay, so if X is 0.5, I will multiply 0.5 with P. But if X is 1.3, then P will be multiplied by 1. Okay, because 1 will become the minimum. Okay, so this is the whole procedure of how you calculate the level of service for a signal. Now before we proceed, do you guys have any questions? Anybody has any questions? Okay, I'll take it as a yes. Moving on. Okay, so we have very small question, uniform delay for one through only lane. So one lane means one lane group only. Okay, so we have to find out uniform delay for that lane. Okay, so we have cycle length, effective green, flow is given, saturation flow rate is given. So it's already, they have already done the calculations for that, and the arrival type is 4. Okay, so if I go back to the D1 equation, I need the progression factor. Cycle length is given, G by C ratio is given, and X is not given, but I have the flow rate. Okay, so first of all, let us calculate the X. Now X is V by C ratio. Okay, V is given, V is 700. I need to calculate capacity. Capacity is number of lanes, S, and G by C ratio. I have one lane only. Okay, so C is 1 multiplied by saturation flow rate multiplied by G by C ratio. How much is this? Yes. How much is the capacity? $80 only. How come? 1800 multiplied by this. It's too low. Yes, okay. So 0 means alert. Zainab? 0 means alert. Okay, then we calculate the V by C ratio 700 divided by 800. How much? Okay, so now we can move on. Another thing which I need is the proportion of vehicles during green, so I need the arrival type 4, arrival type 4, RP factor is 1.33. So I'll put RP here and G by C I already know. So P is 1.33, the RP factor, G by C ratio. How much? Okay, so now we can, so we have the P factor. Now we can use this big equation for progression factor. So progression factor 1 minus 0.591, the P value, 1 minus G by C ratio multiplied by 1 minus gamma. Okay, let me calculate the gamma first. Okay, I'll just write gamma. Okay, so minimum of 1 or x, my x is 0.8 sine 5, less than 1, multiplied by G by C ratio. So how much is this? Okay, so now we can move back. So I need in gamma here 1 minus 0.388, 1 minus 0.875, 40 by 90. Oh, sorry, P value. What is my P value? 0.591 multiplied by 1 plus gamma 0.388, 1 minus 0.591 to 90 divided by 40. I put all this, bracket. Okay, you can refer back to this equation, just take the values from here. Okay, this is the equation I'm using. Okay, I've tried to write it as best as I can, but okay, so we have all the values in the chat. Yes, anyone calculate the value? Okay, thank you. So now we have the PF factor 0.72 into something very big, 0.5 into 90 to 1 minus 40 upon 90 square 1 minus my x is 0.8 something 75 to 40 by 90. Yes, anyone? The delay. Okay, now for this particular lane group, if the delay is 16.4, then we have level of service B. But this is only for this lane group, okay? The same could be done for the entire signal as well, and we will do it later on for the entire signal. Okay, anyone has any questions at this point? Okay, moving on, we are still continuing with the topic of the signal. And now we will look at the design of the signal. Okay, and now signal is the only type of traffic control device which you can completely analyze and design, because everything is happening according to signal timings. Okay, so that's why you will find a lot of material in the textbooks as well as in the other studies and reports about signals, because with the stop signs and uh, roundabouts and these things, you can just imagine, okay, or you can just design, okay, that it will be safe at this point, and we are giving this much time to the driver, this much distance is available, and that's it. But you cannot analyze what the driver is actually doing. Okay, but in signals it is possible because the drivers are following the timings from all directions. Okay, but in areas which have low traffic volumes, we do not usually prefer providing signals, which you may have seen on most of the local streets in Bahrain as well. But when the traffic is very high, the corridors or the routes which have high traffic, the signal also becomes the most important traffic control device there. Okay, because you need to have some intersections there, even in those corridors. You cannot make everything signal free. The components of a signal, okay, you can see it in these pictures. Okay, so we have a controller, we have a mail function unit, we have a detection rack which is attached with the sensors. Okay, we have a field terminal block. Okay, and we have transfer switches and which activates the signal. We have a police switch. Okay, you may have seen the police the police officers, when they go and they control the signal manually, this is a switch they are using, so they don't have to use all the controls on the signal. They just have like a switch to just change the phases, that's it. Okay, so it becomes easier for them. Then you have another type of traffic controller, signal controller. Okay, you have a controller, but the main thing is it has a conflict monitor as well. So somebody, most probably my student, he made a mistake in signal timing calculation or signal timing logic. The conflict monitor will control that. So it will make sure that two conflicting moments are not happening together, even if the programmer made a mistake of putting them together. Okay, so for example, this and this. So even if somebody made a mistake of putting these two in the same phase, the controller, the conflict monitor will take care of it. It will block the movements. Okay, and then later on somebody can see and check what happened. Okay, this is like a definition of what I was showing earlier. The signal controller, it controls the program, the logic of the signal. The mail function unit or conflict monitor. Okay, so they were used in different cases here. You have conflict monitor here, you have a mail function unit here. So both of them are almost looking at the same thing. Okay, some error in the logic or some problem with the signal, maybe one of the lights is not working. So this conflict monitor or mail function management unit will come into play, and it will make sure that everything is going properly. If it is not going properly, then it will change the signal into flashing mode. Okay, so all directions will start flashing. Okay, so drivers will have the warning the signal is not working properly, and the authorities can check the signal and repair it later on. Then we have the detector rack. Okay, so it's a shelf, it's a rack in which they have cards for every movement, a different card for every signal phase. Okay, and it receives the call. The detector rack receives a call from the sensors on the road, and then it tries to calculate the signal timing according to that. So this is basically getting the signal from the sensors or detectors on the road. Okay, so the number of racks is according to the number of sensors you have. Then you have the field terminal, which is providing the connection between the sensors and the signal. Okay, the wiring and everything. Then you have the switches and the relays which are inside the signal. So when the signal comes from the detector rack, it goes to these relays and switches. Okay, so what these relays and switches are doing, they are transforming the signal of the program into the signal lights. So these switches are basically turning off and on the lights according to the signals received from the sensors and detectors. Okay, so they are of different types. Okay, switches, switches. Okay, they on and off. Relays are, they produce the pulse which causes the switch to go on and off. Okay, so switches are going on and off with the pulse. The pulse is sent by the relays. And then we have the flashers, which work when the signal is not working properly. So you don't need the switches, then you need the flasher. Okay, because switch will turn off or on, but the flasher will blink the light. We have the police switch, I already explained it. Okay, so information, sensors get the information from the field, and that is done by a sensor on the road, which is normally inductive loop. It goes towards the signal controller. Okay, it goes towards the detector rack, then the controller. The controller will change the lights will let the drivers know who is supposed to move, and after that you will have the movement of cars. When the cars move, further data will be recorded. Okay, so it's like a cyclic process. Okay, the calculation of signal timing follows these 12 steps. Okay, first one is you identify whether you want the left turns to be protected or permitted. We normally go for the protected ones, but there are conditions actually whether you want to make them protected or not. Usually you will not see left turnings as permitted. Okay, permitted means what I told you earlier as well. Permitted means that you clear or you move from the intersection when it is clear. Okay, so normally what we do is if the left turning is permitted and we feel it will be too dangerous, we keep it with the straight then. Okay, so step one is basically whether you want a separate phase for left turning or you want to keep it with the straight one. Okay, in most of the cases it goes in like this, because in a city, if some signals have permitted left turnings, okay, and some signals have protected, it will be very confusing for the drivers. Okay, so what we do is, the practical solution is, on signals where you want to make them permitted, to avoid confusion, we just keep it with the straight. Okay, obviously when the straight goes, drivers may find the left turning allowed as well. Okay, and so on and so forth. Then you identify the lane groups. Okay, so which lanes can be grouped in one set in each direction. Okay, and I told you for the lane groups, all movements must be same. So if you have two lanes, both of them only left turning, this will be one group. You have one lane which is for straight, one group. You have another lane which is straight and right, another group. Okay, so you will have number of lane groups. Then for each lane group, now everything from step 3 onwards is for lane groups. Okay, from step 3 onwards, you work according to lane groups. Okay, so for each lane group, find out the demand, find out the saturation flow rate. So you can calculate the demand upon saturation flow rate ratio. Now this is demand upon saturation flow rate, not demand upon capacity. It's not V by C, it's V by S. Okay, so V by S ratio. Then you develop the phasing plan using V by S ratio. Okay, I will show you how. Then you calculate the red and yellow timings for each phase. Then you calculate the lost time for each phase and then for the whole cycle as well. Then you calculate volume capacity ratio for the signal. So this is the V by C ratio now. So first one was V by S. Okay, then you have what else? Yeah, oh sorry, for the seventh step, you select, because you are designing, so you have to select a V by C ratio. Okay, now what value of design V by C ratio we should use? If you use V by C ratio of 1, that means peak hour volume equals to capacity of the signal. So if I put V by C ratio 1, then demand will be equal to capacity. Okay, so I want the V by C ratio to be less than 1, so demand will be less than capacity in the peak hour. Okay, so we select a ratio which is less than 1, but it doesn't mean that you select 0.1 or 0.5. This is too low, so we select something which is close to 1 but not 1. Okay, there are ranges given for that. I will show it to you. Then you calculate, after you selected V by C ratio, you will calculate cycle length. From the cycle length, you calculate effective green time. I told you effective green time is cycle length minus the lost times. Then you distribute the effective green time into different phases. Then you calculate the actual green time, and then you will check the pedestrian requirements. Okay, let us go through these steps one by one. Okay, first thing is, I told you the first step is find out if you want to make the left turning permitted, protected, or a combination. Okay, and I told you combination confusing, permissive can also be confusing, and it can be dangerous as well. So basically what we are saying is, do we need a separate left turn for separate phase for left turning, or we keep it with the straight? Okay, this is the question we are trying to answer. Okay, so what are the conditions? You have three conditions depending upon number of opposing lanes. So if I'm talking about this left turning, then opposing lanes are these opposing lanes. Okay, so if you have one opposing lane, okay, you will see left turning multiplied by opposing volume, this volume, straight volume. If you have a right turning will not be counted here for this multiplication. So you will multiply the left turning volume with this volume. Okay, and if it is one lane, then this volume must be more than 50,000 to provide a separate phase for left turning. If there are two lanes, then this volume must be more than 90,000. There are three lanes, then must be more than 110,000. Okay, we don't have more than three lanes here. More than three lanes means that you should provide a separate phase for left turning, because left turning will be too long. If you have more than three lanes, and so you don't need a check in that case. Opposing lanes, okay, if you have more than three opposing lanes, you shouldn't do a check. Okay, there should be a separate phase for left turning, because left turning will take a very long time. I have to cross all the lanes, right, for left turning. So if I have four lanes, I have to cross four lanes to get to the other side. And if you just keep it with the straight, it will be very problematic. Okay, so more than three lanes left turning signal will be required separate. So this is the numerical criteria. Then we have some other criteria as well. Okay, some warrants. First warrant is side distance. Okay, people who are turning left, they don't have enough side distance. Okay, so the other road has a curvature, or the gradient is very steep, so they cannot see the other side properly. Then a left turning signal must be separated. The opposing traffic has high speed, 45 miles per hour or more. Okay, so then it becomes dangerous to keep the left turning permissive. Presence of more than one left turn lane. So you already have very high volume left turning, and you decided you will provide two lanes there. So again, you cannot allow multiple vehicles to make the left turning without any signal. It is dangerous. Okay, and having a crash history for left turning vehicles. Okay, so all these are safety related criteria. Side distance is related to safety, speed is related to safety, more than one left turning also related to safety. Okay, because you have two vehicles going side by side without any signal, and vehicles are coming from the other side as well, is dangerous. Okay, and crash obviously is related to safety. Okay, so in this case you go for the left turning separate signal. Then you have to identify the lane groups. I've already mentioned this. I've shown this earlier as well. Okay, so let me ask you something. If I have this, and this, how many lane groups I have here? In this case, how many lane groups I have? I have three lanes with these movements. How many lane groups I will have? Yes, anyone? Is it one lane group or two lane groups or three lane groups? How many? Three lane groups. Anyone else agrees with her? Dana, Zainab, do you guys agree with her? She is saying we have three lane groups here. Yes, Dana. Hand raise means you agree. Three. No, we have two lane groups. Okay, we have two lane groups. We have two lane groups. These two, one group, and this one is, so this is one and this is two. Okay, when lanes have exactly same movement, they are in one group. Okay, because their capacity will be same. This is the idea behind the lane group. Okay, when you have lanes having exactly same movement, you will put them in one group. You will not put them in separate groups. We don't have three lane groups. We have three lanes, but two of them belong to the same group because two of them will have the same capacity and the same saturation flow rate. Okay, everybody got the idea? Do you have any questions, any confusion? You understood the difference between number of lanes and number of lane groups. So you can pack up multiple lanes in one group if their capacity and their movements are same. And yes, capacity will be same if their movements are same. Okay, so I have two lanes here with same movement. Okay, and I have another lane which has one extra movement. So these two will have the same capacity. So I can take capacity of 1 multiply by 2. So this will make one lane group. For this one I have to calculate separate value of capacity. Got it? Any questions? Any problems? Any confusion? Okay. Then for each lane group you will find out the saturation flow rate. In the last lecture we did an example for saturation flow rate. So you have a base value 1700, 1900, 1800, and then you will multiply with the value with the adjustment factors. Okay, we looked at the adjustment factors. So for every lane group you will do this, and for every lane group you will calculate the demand as well. Demand comes from the field. The demand comes from the design data. So somebody will tell you I want a signal at this intersection, okay, and I will have these many vehicles straight, these many turning left, these many turning right, these many from this direction, this direction. Okay, so this is input data. The demand volume is input data. What you are calculating is saturation flow rate, and for saturation flow rate we have a base value which is multiplied by multiple adjustment factors. Okay, now for example I gave you this example. I have two lane groups. Okay, so there will be a saturation flow rate for these two lanes same, but there will be one value here and one value here, and for each of these lanes I will have the demand flow rate, and I will have the demand flow rate for this one as well, and for each of them I will calculate V by S ratio. So in this case V by S, the S will be the same for both the lanes. Okay, so I will have V by S for this one, for this one, for this one. Okay, and now for the design of the signal, all three lanes have the straight movement. So when I will design a phase for a straight, all three lanes will move. All three lanes will have the cars allowed to move. Okay, but their V by S ratio is not the same. For these three lanes, the V by S ratio is not the same. So I'll pick for design the V by S ratio which is the most critical one. The critical one is the highest one. The critical one is the highest one. The lane which has V by C, the highest V by S ratio, will be picked as a critical one for each phase. So all three lanes will have one phase, okay, which is for the straight movement. But all three lanes don't have the same V by S ratio. So for my design, I need one value of V by S. I will take which value? The one which is the highest one, the critical one. Okay. So for every lane group, you will calculate V by S, and you will see which lane groups will go in the same phase. And for that phase, you will pick the most critical one for the design. Okay. Then you need to, once you have done that, you will develop your phasing plan. So which movements will go together and so on and so forth. Once you develop the phasing plan, you will sum the V by S ratio for all the critical lane groups. Okay, so I have a critical lane group in this direction, in this direction, in this direction, in this direction. Okay, so this one is, let's say, 0.9, this one is 0.7, this one is 0.2, the critical one. Okay, and this one is 0.4. Okay, so the critical one for each phase. I will add them together. Okay, I will develop the phasing plan. From each phase, I will pick the critical V by S ratio, and I will take the summation. Okay, and I should try to make the phasing plan in a way that the V by S ratio summation is the least one, minimized. Okay, so my objective function is to minimize the sum of V by S ratios. Okay, and the V by S ratios are only summed for critical lane groups. Okay, not all of them. Don't worry, we will go through an example in which these things will become more clear. Okay, these diagrams are basically showing you some notations we follow when we are coding the movements. Okay, so for example, the straight movements are always coded with even numbers. Straight movements are always coded with even numbers. The left turnings are coded with odd numbers. Okay, so even numbers for straight and odd for left turning, and right turning is coded as 10 plus the coding of straight. So if straight is 2, the right turning will be 12. Straight is 14, the right turning, sorry, straight is 4, the right turning will be 14. Okay, and so on and so forth. Then we have the pedestrian movement. Pedestrian movement obviously is crossing the street, right? So we represent it with P. Okay, and the numeric number is given for the movement which will go in the same direction. So you see 2p here. Okay, why? Because there's 2 here. Okay, for the straight, and these pedestrians will cross with this straight, right, in the same direction. So 2p. Okay, then we have 6p because these will cross with this movement. So this movement is 6, so 6p. Okay, so these are some notations which we follow for coding the movement. Okay, but this is just recommendation. You can make your own codes. Okay, you know, till you remember it and you don't have any confusion for it, any coding is allowed. Okay, so these are just recommendations. Then you start calculating the yellow time and the all red time. Okay, yellow time we know. Okay, now we have two yellow times on our signals. We have yellow time when signal goes from green to red, and we have yellow time when signal goes from red to green. Okay, so according to you, which yellow time is more critical? More dangerous, risky? Green to red, red to green. Yes, which one of them is riskier? Yeah. What about the other three? Other two, by the way. I'm the third one. Yeah, what about the other two students? You don't have any opinion? Who will not vote here? Okay. What about the remaining two? Go ahead. Or remaining one. Who is left? Is it Zainab or Zan or Dana or other Zainab? Who didn't vote here? Go ahead. Okay, so as you said, green to red is more critical. Okay, so we are talking about yellow, which goes between green to red. Okay, so yellow is also called as change interval, and clearance is also called as all red interval. Okay, so there are two names for each one of them: yellow or change, and all red or clearance. The yellow is for the dilemma zone. Okay, what do we mean? You are coming close to the signal. Okay, and you need to decide whether you should stop or not because signal has just turned yellow. Okay, so yellow time should be enough for a driver who is in the dilemma zone. If you are very close to the signal, obviously you will not stop. So if you are just like 10 meters away from the signal, your natural reaction is I will not stop, I will just move. Okay, if you are very far from the signal, so you are already 100 meters away from the signal, so if signal is yellow and your reaction is, you will most definitely stop. But what about the person who is in the 40-50 meters zone? That is a dilemma zone because that person can decide either way. His judgment can be either way. This is what we mean. Okay, so yellow is for that person who is in the dilemma zone, who is near the edge of the stopping distance. Okay, so he is coming at high speed or whatever speed, and he has both the decisions available. He is not very close and he is not very far as well. So that is called the dilemma zone. So people in the dilemma zone should get enough yellow time to look at the yellow signal and decide, and basically we assume that they will go the most critical case. But if they decide to stop, obviously they have enough distance to stop as well. So yellow is for somebody who is in the dilemma zone, which is very close to the stopping distance, and the yellow is enough for that guy to cross the stop line. Okay, if you look at the slides and you can go to the link. Okay, you can see a dilemma zone, it has a link, dilemma zone protection text here, it has a link. You can go to this link and maybe the video will play. Anyways, you can search for it on the internet as well. Okay, can I play it? Let's see. No, I cannot. Anyways, something, let's close it. Okay, but you get the idea. Okay, then we have all red. All red is also called a clearance interval, which is for vehicles which are in the intersection already. Okay, and we want them to clear the intersection because before the next signal becomes green. So you crossed in yellow, basically you crossed in yellow, but you could not reach the other side and your signal has become red. So if the next one becomes immediately green after your red, the next one becomes immediately green, then there's problem for you because the next guy may directly bump into you. Okay, so we hold the next guy for a few extra seconds to give you time to clear the intersection. Okay, so this is the time when we have all red. Okay, so your signal is red and the next one is waiting on red for few extra seconds. Okay, so all the signals are red. Okay, so this is called as all red or clearance interval. To calculate them, we have this equation. So this equation, you can see it has two parts. This is called as clearance interval, which is yellow and all red. Yellow plus all red is total called clearance interval. Okay, yellow is the first two parts of the equation, and this is the all red part. Okay, so this is all red and this is the yellow part. This TPR, perception reaction time, you have used it in highway engineering for calculating a stopping sight distance, same value. S naught, speed of the vehicle on the for the lane in which for which you are calculating this. A is the normal acceleration of the vehicle or deceleration of the vehicle for stopping, which is taken as 11.2 as per AASHTO standards. Capital G, gradient. Small g is the gravity. So it's no longer effective green here. It is the gravity because it's coming from the stopping sight distance equation. In that equation, small g is gravity and capital G is gradient. Then we have the all red part. This is width of the intersection. This is length of the vehicle. So width of the intersection, length of the vehicle. And then we have S naught, which is speed. Okay. So if you are calculating, if you have this intersection, okay, and I'm calculating for this movement, okay, so this will be W. This is my W value. Okay, and length of the vehicle is length of the car. Okay, 18, 19, 20 feet, something like this. Okay, default, as you can see, is written here 20 feet. Okay, in some books they have taken 18 as well, no problem, but it's obviously it's a standard value, right? Width of the intersection you will change, okay, for every movement and for every intersection. If I do it for this direction, then my W will be from here to here. This will be my W. Okay, so W will change. Okay, but L will remain the same. And S naught, okay, obviously will change according to the direction and the movement. Okay, so once you have done that, you go and calculate the lost times. There are two types of lost times: startup lost time and clearance lost time. Every phase has two lost times: startup lost time, clearance lost time. You can see them here in this figure. Okay, it's a very nice picture. So this is green interval, so signal became green. Before this one it was red. Okay, it became green, then it remained green, then it became yellow, then this one is all red. This one is all red. Okay, so when the signal became green, you will not move immediately. You will take some time to, you know, put your phone away and put your coffee away and get your car moving. The car will take maybe 1 or 2 seconds to start moving. So this is your startup loss time. Okay, when the extra time the car is taking to start moving. And all the cars, most of the cars will do it, right? The first 3-4 cars, they need this time to get moving. The cars which are behind, they already see the signal green, so they become ready. Okay, so the startup loss time is in the first 3-4 cars. Then this is the clearance loss time. Okay, clearance, not clearance time, clearance loss time. Okay, so all red is obviously clearance because your signal is red. But if you are far from the signal, you may stop at the last second of yellow. So the last second, 1 second, 1.5 second of yellow, because of your caution, because of your care. Okay, because you want to take, you don't want to take risk. This is what you should do. Okay, I mean, most of you may not be doing it, but this is what you should do. Okay, we should do. Okay, so don't take a risk on the last second of yellow that it will remain yellow. You don't know. Okay, so when the signal is yellow, the normal behavior should be that I should stop even before the yellow becomes red. So that's why you see a small portion of yellow in the included with the L2 with the clearance loss time. Okay, so you stopped in the last second of yellow. You didn't want to take a risk, okay, that I crossed during red. And obviously there's a camera and all these things as well. Okay, so the all red time is part of L2, and the last 1 second, 1.5 second of yellow is also clearance loss time, because nobody is going inside. Okay, so the extra time taken by the first 3-4 vehicles of the queue to get moving, and the last few seconds are not used by any vehicle to enter. So these are the two loss times we have. Okay, their values are given: startup loss time 2 seconds, clearance loss time 1 to 2 seconds. So you can add them together to get the total loss time of one phase. Okay, then you can do the same for all the phases. So if you have 4 phases, you will add 4 of these timings. Okay, then in this way you can calculate the effective green time as well. Just remember this equation. Okay, we will not calculate effective green time now because we did not calculate any green time yet. So this equation, what we have covered up till now, this equation does not have all the values which we need. Okay, but for example, if somebody gave you green time this time, when you see the green bar, okay, so when you see the green bar, somebody gave you this time, and you have to calculate small g, effective green time. So what we do is, you take the green bar and the yellow bar and the all red bar, and then you subtract L1 and L2. This will give you effective green. You can see it over here. They have taken total green, yellow, all red, and subtracted L1 and L2, which will give you effective green time. Okay, so this is how you will calculate effective green time. So later on we will use it in this way. Okay, but right now we haven't calculated green time. Right now we don't have enough data to calculate green time. Okay, it will come after. Then you select a V by C ratio. Okay, and what did I say about the V by C ratio? Okay, volume capacity ratio, what it should be? Yes, what about the other three? More than one? Somebody changed their mind, huh? 1. Okay, it should be less than 1. Okay, should be less than 1. B by C means demand upon capacity, right? You want the capacity to be more than the demand. So B by C ratio should be less than 1. 1 means they will be equal. Equal is risky. If B by C ratio is 1 or very close to 1, it is very risky, because you will design now and the signal will work in real time in future. So in real time, you may not have exactly the same demand which you estimated. You are forecasting, yeah, you are estimating. So the actual can be different than your estimate. Okay, so you want some cushion, you want some factor of safety. So if demand is lower than my estimated demand is lower than capacity, then I have some margin. Even if I was wrong by 5-10%, it will still reach capacity, not go above capacity. So we don't make it 1 or even close to 1. So we keep a margin of error of 10-15%. That means V by C ratio is 0.85 to 0.9. 10-15% from 1, right? 1 is absolute equality. Okay, so we need some extra capacity. How much extra? 10 to 15%. That means the V by C ratio will be 0.85 to 0.9. Okay, so having V by C ratio of 1 is very risky. Okay, then once you have all these values, you can calculate the cycle length. Cycle length has 2 equations. Okay, you can use one of them or both of them. This one is which one? This one. This one is more commonly used. Okay, and this one is empirical equation given by Webster. It's an old one. Okay, but this one is the new one, the latest one. Okay, so we have L, which is the total lost time. So remember, each phase has two lost time. You add them together, you get lost time of one phase. Then you add the lost time of all the phases, you get L, capital L. So capital L is the lost time of the entire cycle. Then you have a XC, the V by C ratio you have selected, and then you have the V by S ratios, the summation of V by S ratios. Remember, every phase has a critical lane, and that critical lane has a V by S ratio. When you add the V by S ratios of all the phases, critical V by S ratios of all the phases. Okay, so that is summation of V by S. Okay, same thing here. L is the lost time, V by S is V by S. Okay. If you are going for a pre-timed signal or a semi-actuated signal, pre-time means no sensors, semi-actuated means half sensors. Okay, sensor is only half of the directions. So then you go for a lower V by C ratio because we need more margin. You don't have any way to see or monitor the real-time traffic. But if you have actuated signals, I know there's a sensor. The sensor gives me real-time observation. Signal timing is according to real-time traffic. Then in my design, I can keep a higher V by S ratio. I don't need much factor of safety here. Okay, so when I'm uncertain, I don't have any way of monitoring real traffic with pre-timed and semi-actuated, then I keep higher factor of safety. So V by C ratio will be lower. And when I go for actuated signals, I keep higher V by C ratio because I can actually monitor real-time traffic and the signal is already operating on or adjusting according to real-time traffic. Okay, once you calculated the cycle length from any of these equations, cycle length minus lost time will give you total effective green. Cycle length minus lost time, total lost time. Okay, so total time of the cycle minus total lost time will give you total effective green. Okay, once you calculated total effective green, you will divide the effective green into different phases according to their V by S ratios. Okay, but for example, if my cycle length is 120 seconds, so one of these equations gave me 120 seconds. Okay, my lost time for one phase is 4 seconds and I have 4 phases. So in each phase, lost time of 4 phases, cycle time 120 seconds. Okay, so what will I do to calculate effective green time? First of all, I will calculate my total lost time. So 4 for each phase into 4 phases. So 16 seconds of total lost time. Then effective green time total is cycle length minus total lost time, which is 120 minus 16. Okay, so my total effective green is 104 seconds. Okay, then you use this. So this is what now? This is total effective green, the value which I just calculated. Okay, so you will do it, you will take this value for each phase, multiply with the V by S ratio of the critical lane of that phase, divide by the overall V by S ratio. So the lane which has higher critical ratio will get more green time. The lane which has lower will get less green time. Okay, obviously this is a constant. This will remain 104 in my case for this example. For this example, it is 104, right? So it will remain 104 and summation will remain same value. Okay, so the only thing changing is this one. Okay, so when this goes higher, G goes higher. When this goes lower, G goes lower. Okay, and this is how you get the effective green time for each phase. And then I told you, once you have the effective green time, you can calculate the total green time. So the relationship between effective green time and total green time was this one. G plus yellow plus all red will give you effective green time plus the lost time. Okay, so now you already have the lost time, you had the effective green time, you have yellow and all red, all of them. So the only unknown is capital G. Okay, so this is how you calculate the capital G here. In all cases, some ranges are given cycle length should be between 40 and 180. So if your equation goes out of the range, you can take the minimum or the maximum from the range. Okay, G value for different movements. For major street, capital G, green time, the green bar, okay? The green bar should not be less than 15 seconds. For minor streets should not be less than 7 seconds and so on. So if you calculated green time is less than 50 seconds, a major street will take 15 seconds then. Then the last thing is to check for pedestrian clearance. The green time you are providing for the vehicles, can pedestrian move in the same green time in the same direction? So if I calculate green time for this direction, so can the pedestrians who are crossing in this direction use this green time to cross the entire road? This is the check. So green plus yellow plus all red for this direction. So this is called as the phase timing. This entire thing is called the phase timing. So the pedestrian time should be less or equal to the phase timing I am providing. Okay, the time the pedestrian requires to cross the road should be either equal to the phase time of the vehicles or less than that. Okay, so they will have extra time. So how do I get the minimum time for the pedestrians? We have walking time and flashing don't walk time. Okay, walking time is the time they need to cross the road. Okay, it's given between 5 to 7 seconds, and the flashing is calculated using the width of the road. I told you width is, if they are going in this direction, then the width is from here to here. Okay, this is the width, and divided by the speed of the pedestrian. So this is the speed of the pedestrian. Again, for the speed of the pedestrian, we have some default values. Okay, 3.53 normally these. Okay, so this will give you how much time the pedestrian needs, and then you compare it with the time which you have already calculated. You calculate yellow, green, and all red. So you add them together, compare it with this one. This combination should be higher or equal. Otherwise, you need to change the signal timing. Okay, pedestrian, it's not safe for the pedestrians. Your signal is not safe for the pedestrians. And the pedestrian speed, since for example somebody did not give you these values, 3.5 second, 5 second, 3 second, 3 feet per second, somebody did not give you these speeds. You want to get these values yourself, you can go in the field, record the speed of the pedestrians, and then you take the 15th percentile, meaning the speed of the 15th slowest pedestrian. The 15th slowest pedestrian. Okay, the 15th lowest value. From all the speeds, you take the 15th lowest value. Okay, so very close to the worst case. Okay, in Pakistan we used to have traffic engineering course in which we used to have this experiment. Students used to go in the field and do this. Okay, so